questions that we did not yet go over in class, so we are going to look at those now. The number 7, we skipped over this because we were running out of time. It says the total number of students on a school bus since the route began is given by, that probably should just say R, a differentiable function of the minutes since the bus route began. Which of the following is the best interpretation of R prime of 30? So we first need to think about what R stands for, and it's the total number of students on the school bus. So R prime is the rate at which the students get on the bus. So we're looking at 30 as our time. So after 30 minutes, exactly 30, during the first 30 minutes, exactly 30 minutes after the bus route began. And then down here, scroll down there. There we go. The rate at which the students here. This is part D, does not have a time. It doesn't include that 30 anywhere, so that's not our best answer choice. Also, B is not a good answer choice because it says during the first 30 minutes. Whenever we're looking at a derivative, it's an instantaneous velocity. So we're talking about our instantaneous rate. So at that point. So A or C are probably our only possible correct answers. So A says after 30 minutes there were 11 students on the bus. This would be the answer if we were talking about R of 30, because R tells us how many people are on the bus. R prime is a rate. So exactly 30 minutes after the bus route began, students were boarding the bus at a rate of 11 students per minute. So that would be our answer C there for this problem. We did 8 together, and I believe we did 9 together. So we're going to look at 10. So 10 is a person 6 feet tall walks away from a street light that is 10 feet above the ground. If the person is walking at a constant rate of 3 feet per second, at what rate is the person's shadow lengthening in feet per second? So in this case, we know that we have a street light here, and it is 10 feet tall. And then we have a person that is walking away from that street light. And when we know the rate at which that person is walking away, we want to know what the rate is, at what rate is the person's shadow lengthening. So the light from this street light here would follow this path here, and on the ground here we would see the person's shadow. So I'm going to call this length right here X, and I'm going to call this one here Y. And what we have here are two triangles that have to be proportional to each other. So we would have to have this big triangle here would have to be proportional to the smaller triangle that's occurring. Then we know that also, I haven't labeled here, that this man or person is 6 feet tall. So 6 over Y would be the vertical component and the horizontal component of our smaller triangle here. So this would have to equal the vertical component of our larger triangle, which is 10, and then the horizontal portion of our larger triangle, which would have to be X plus Y. So here, eventually we want to take a derivative of this, but it's going to be much easier to do if we sort of simplify this first. So if we cross multiply, we would have 10y equals 6 times x plus y, which we could distribute our 6 here. So 10y would equal 6x plus 6y. And then we could combine those y's. So if we combine those y's, we would subtract our 6y from both sides. 4y equals 6x. So we have a really simple equation here, actually. And we're going to take that derivative, and we're just going to get 4 dy over dx is going to equal 6 dx. I'm sorry, that should be dy over dt. And this will be dx over dt. And so they tell us here, we know that the person is walking at a constant rate of 3 feet per second. So x is going to be changing at 3 feet per second. That's our dx dt, because that length that the person is away from the base of the street light is going to be increasing at that rate. So our dx dt we know is going to be 3. So we will have 4 dy dt is going to equal 6 times 3. And so if we just solve here, we got 4 dy dt is going to equal 18, and we would just divide by 4. And so 18 divided by 4 is going to give us 9 over 2. Or if you want to just do 4.5, that would be fine. So we would say 4.5. That would be measured in, I believe it's feet. Let's make sure. Feet per second. Okay. Let's move on to the next one. So let me change this so we can see this whole problem. Okay, so a ferry is traveling back and forth on a straight route from the mainland to an island. The velocity of the ferry is shown below. At what time does the ferry change direction? So remember that if our velocity is positive, we will be traveling in one direction. If our velocity is negative, we'll be traveling in the other direction. So we could think of it as like north and south, or east and west, up and down, whatever you want to think of here. But the velocity of the boat is positive all the way up until 6. It does hit 0 here at 4, so the boat does stop at time t equals 4. But it doesn't change direction because its velocity is still positive right here. But right here we go from positive to negative, so that is the time when the boat changes direction. So it would be at t equals 6, and they don't give us units here, so that could be hours or minutes, or I'm not sure what we're talking about here, but since it doesn't give it, just t equals 6 is what you need. Okay, this next one is a tangent line problem that has a little bit of a twist to it. So let f be a differentiable function such that f of 2 equals 1 and f prime of 2 equals negative 2. If the tangent line to the graph of f at x equals 2 is used to find an approximation to a 0 of f, what is that approximation? So if we kind of think of what's happening here, we know f of 2 equals 1. So we know that our function goes through here. We don't really necessarily know exactly what it looks like, but we're going to draw a tangent line at that point. We know it's going to pass through that point. So we would draw our tangent line here. And so since we can't actually find our 0 here, what we could do is we could find the place where the tangent line crossed the x-axis, and that would be our estimate of the 0. So to do this, we will need the tangent line at 2. So our point f of 2 equals 1. So the point 2, 1 is our point of tangency. And then f prime of 2 equals negative 2. I've drawn this picture wrong because that should have a negative slope there. This will be our slope. And we would have y equals negative 2 times x minus 2 plus 1 would be our tangent line. So what we want to know is we want to know where this crosses the x-axis. And if we want to know where it crosses the x-axis, then we would plug in 0 for our y. So we would have 0 equals negative 2x plus 4 if we distribute here, plus 1. So we get 0 equals negative 2x plus 5. We'll move that 5 over, so negative 5 equals negative 2x, and then divide by that negative 2 there. So we would get 2.5 or 5 halves as the approximation for our 0. So it would be approximately x equals 2.5. And we've got a couple more that we're going to look at. And so pretty much any limit that you see, especially if it is on free response, you pretty much want to treat it like it is going to be Lipitor's rule. So if we did this problem here, if it's going to be Lipitor's rule, we want to do the limit as x approaches 0 of e to the x plus 4 minus e to the 4th. And when we do this, that's going to be e to the 0 plus 4 minus e to the 4th. Well, that, of course, is just e to the 4th minus e to the 4th, which gives us 0. And in the bottom, it doesn't even seem like we would have to write this, but we do. Limit as x approaches 0 of x is 0. So here we're getting 0 over 0. So we would say Lipitor's rule applies. It is required that you show that step where you're showing that Lipitor's rule applies. So then you can take your derivative. So when you take the derivative of the top and bottom here, the derivative of the top, e to the x plus 4 is e to the x plus 4. You do have to multiply by the derivative of x plus 4, but derivative of x plus 4 is just 1. Derivative of e to the 4th is 0 because e to the 4th is just a number. E is like pi. That's just a number, so we'll get 0 there. And then in the denominator, derivative of x is just 1. So if we plug in 0 to this, we'll get e to the 0 plus 4 over 1. So we're just going to get e to the 4th as our answer. And we've got one more. I think just one more. Is that true? Yes. One more that we're going to look at here. And this is another Lipitor's problem. So we've got limit as x approaches infinity of natural log of e to the 2 times infinity. Oh yeah, actually I should not write. I shouldn't plug that infinity in yet. Just write 2 to the x plus 3x. And so this is going to be natural log of e to the 2 times infinity plus 3 times infinity. So here you just have a really large number because you got e to the infinity plus 3 times infinity. And even when we take the natural log of that, we're still going to get infinity there. And then in the denominator, when we do the limit as x approaches infinity of x, we will also just get infinity. So for this one, Lipitor's rule applies. And we want to take the derivative of the numerator and denominator here. So we're going to have limit as x approaches infinity of, when I take the derivative of natural log of all this stuff, I'm going to get 1 over e to the 2x plus 3x. But then I have to multiply that by the derivative of what's on the inside. So that is going to be e to the 2x times the derivative of 2x, which is 2, plus 3. And then this is all going to be over the derivative of just the x, which is 1. So we could go without writing that. Let me change this so it doesn't get too small. And so here we've got the limit as x approaches infinity of 2e to the 2x plus 3 over e to the 2x plus 3x. And so here we have a Bobo-Botno situation. In this case, it was difficult to do that on the last problem, on the original, because you had that natural log in the e. So that kind of made it difficult to see what was going to happen here. But now we've got an e to the 2x on top and bottom, and that would be considered our highest degree. So since those are identical, we're just going to divide our coefficients, and we will get 2 for our answer here. So that'll be our answer for that one. So hopefully this is a little bit helpful. You'll see some of this on the test tomorrow. So if you have any questions, try to ask each other and help each other. I might be able to answer some questions if you can email me, just depending on how I'm feeling.